Okay. Question?
I just have a question.
Yeah, great. Can we look at it or you?
I don't get. I did better, I think, last year.
Okay.
So I'll do that.
The trick there, so this is an antiderivative question.
Yep.
I don't remember.
Yep.
So, and whether, whether it's little f and you're looking for capital F, or f prime and you're looking for f, or f double prime and you're looking for f prime, right? It's all the same question. What is the antiderivative? And the sort of secret is to rewrite this as x to the 1/2. So when we're looking at antiderivatives, we have a pretty narrow range of functions that we're able to find the antiderivative of. And if it doesn't fit sort of one of our standard patterns, we don't have a lot of other choices. We don't have product rules and other sorts of things. So we want to rewrite this or think of this as two separate antiderivatives because it's a sum. So that's nice, right? We're not worried about sums. We can deal with them separately. We're also not worried about constant multiples. Those don't change the kind of structure. We can just hold those out and just focus on what's underneath. So the antiderivative of x to the 1/2, that's a power rule. So I'm going to add 1. 1/2 plus 1 gives me 3/2. And I'm going to divide by that 3/2. This is kind of a separate process. It's a separate antiderivative. I'm looking at the antiderivative of cosine. We know cosine and sine are related to one another, so we would think the antiderivative of that cosine would be sine. We do want to check and make sure our positives and negatives work out, right? So that's an easy one to sort of mess up. But we know the derivative of sine is cosine, so that works. And then this one, when you do these enough, we want to rewrite this. So we're going to multiply that by the reciprocal. And what else do I need?
C.
Plus C. Super easy to forget, right? But it needs to be there. Okay. Any other questions? Okay, let me jump back into our work with the area. We had, on Monday, we had a definition for what area was. And we said, if f of x bigger than or equal to 0, the area under f of x is equal to, I want you guys to see if you can write it down. we will have to do this eventually. See if you can do it without cheating. Cheating is too strong, right? Peeking at your notes. How about that? And when you write down this definition of what area is, we also want to make sure that we don't just have it memorized as a list of symbols, right? But those symbols have a meaning for us, right? We understand what the definition, the parts of the definition are doing. That's important for us to be able to set it up and to work with it. So this is going to be a limit as n goes to infinity of a sum from I equals 1 to n of f of x of I times delta x. And that is the definition of the area. And when you look at that, you should see this as being, this is a height times a width. So this is an area of a little rectangle. This is adding up n rectangles. It might be 5 or 10 or 100, right? This is adding them up. And then this is letting the number of those rectangles go to infinity, right? So that approximation is closer and closer and closer. The limit is where it is going towards. In order to actually compute this, we need to know what delta x is and what x of I is as well. So these are not, I would say those are really part of the definition as well, because what is x of I and what is delta x? And those are not clear unless you define what those are. Remember, delta x is b minus a divided by n. The width of my interval divided into n pieces. And x of I,
Any point on I?
so that's a point in, so you could, in terms of the definition, you could just say that's an x value in the ith interval. It'd be perfectly fine for the definition. But for actually computing it, we need some sort of formula for it. And the standard formula, we start with a, that's my left boundary, and then I add I times delta x, right? If I'm in the fifth interval, I want to add 5 delta x's to get to the fifth interval. So this is the definition of what area is for us. And we want to be able to do these. We'll keep working. We saw a couple of these on Monday. We'll look at another 1 or 2 of those moving forward. Remember, to do this, you have to kind of calculate these, put them into this function, do some algebra, and then remember our summation tools, and then finally take the limit, right? If we can do all those things, we get a number, right? And that number at this point represents area to us. We are going to think a little more before I get into those details. And the thinking is going to be generated by a new definition. We're going to call the definite integral of f of x. We're going to use this symbol. So this notation is called the definite integral of f of x. And at this point, and really, this will come into play later, but this is sort of the definite integral part. And then this is the function, right? So think of this dx, this is really a big S, if you want to think of it that way. And a and b, these are all part of the definite integral symbol. Just like when you take a cube root, right? There's like a symbol and an index, and all of that combined means cube root. So all of this part, the dx, that's the definite integral symbol. And what that means, what that is equal to, is the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I star times delta x. And you should be saying, wait a second, that's the same thing that we had for area. And you're almost right. The only difference here is that we are not putting a restriction on the function being positive. So for the definite integral, we're just saying it is this limit of sums. These are called, this is called a Riemann sum. It may pop up a little bit in terms of vocabulary. It won't be too important for us. It's just the name of that thing. Right? So this is a limit of Riemann sums. That is what the definite integral is. Now if f of x is positive, then the definite integral is going to be exactly the area under the function. No difference. If f of x is negative, we saw this a little bit on Monday, what we'll get out of this is some sort of net area, like the positive area minus the negative area will give us some value in the end, and it won't be exactly area, but it'll be related to area. So this is a definition, it's notation really to represent what we were already working with. If f of x is continuous on the interval AB, then f of x is what we call integrable, which just means that the definite integral exists. Right, the definite integral is a limit, and we know limits sometimes exist and sometimes don't exist. What this is telling us is that if you have a continuous function, this limit will exist. It will go to some value. Actually also true if you have finite discontinuities, but we won't see those kinds of functions. So we'll be working with continuous functions. Just a little bit more about the notation here. A is called the lower bound. And B is the upper bound. And those are the same as our interval, right? So we're thinking about this function traveling between A and B. What does it look like? And it's doing this calculation, it's just adding up these rectangles. You can think here very much that there's a correlation between this notation and this notation, right? F of x is like our f of x sub I. dx is like our delta x. And this big S is really like our sum. In some sense, this kind of infinite sum. And that's a productive way to think about what this is doing. So you can also think of this as height times width, adding them all up over this interval. The difference in notation is that these values are discrete, meaning they're like chunks. Delta x is a chunk, and x of I is just like these separate values. Here, when we're thinking about the function, we're imagining it as a continuous function. So I'm imagining somehow the dx is infinitesimally small, right? And the f of x is sort of smoothly traveling over this interval. And this is adding it up. So it's doing the same thing, but it's written in a different form. So just a couple properties here about the definite integral. So the integral from a to b of f of x dx is equal to, we're going to call it the net area. So that's what we talked about on Monday, the idea that if the function is above and below, let's say that this area is 3, and the actual area here is 1. The definite integral from a to b of f of x dx, this is my function, is going to equal what?
2.
2. So, and that's the area here is 1, right? We don't actually have a negative area. But when you do the sum, these values are counting as negatives, and it's equivalent to a negative area. So I always feel a little slightly uncomfortable talking about negative area, but it works. The way of thinking about it works. So anything below is going to count as a negative. This is a positive. It's just adding stuff together, so we're going to end up with 2. What is the integral from a to a?
Is 0?
Why?
There's no actual width to it.
Yeah, I think that's a good way of thinking about it. Like if you're thinking about this as being an area, now again, f of x might be positive or it might be negative, so we're not sure it's really giving us area. But if I go from a to a, I'm not going anywhere, it's not going to generate any area. So we can think of the definite integral in terms of area, but we can also think of the definite integral in terms of this definition. If you were to work this definition, where the lower and upper bounds were both a, what would your delta x be? 0. And so you'd be multiplying everything by 0. You can add that up as much as you want, and you're still going to get 0. So just like we want to be able to think about the derivative in a couple different ways, we want to be able to think about definite integrals in a couple different ways. So right now we have an area type definition. We also have a limit of the sum, Riemann sum definition. Right? And both of those are telling us that that should equal 0. What about the integral from a to b of f of x dx plus the integral from b to c of f of x dx? Yeah, do you see what's happening there? If I go from a to b and then I add to that from b to c, that's going to be the same as going all the way directly from a to c. Because both of these are just sums, right? I'm adding up all of the stuff in here, so I can also add this extra bit to it. That's the integral from a to c of f of x dx. We'll make a little note here that this works even if b is not the interval A to C. So it makes sense if B is between A and C, but it actually works even if B is outside of the interval. And to see that, we need one other property here. What happens if I flip the bounds? I think this is one where thinking about it in terms of area is confusing or not very intuitive. But if you think about it in terms of the definition,
It would be the same.
what would happen?
Because you're getting the sums from A to B is the same thing.
You are, except imagine if you actually did the definition. When you calculate delta x, you're going to get the opposite, the negative value, right? Because instead of doing b minus a, you're going to do a minus b, which is going to give you the negative of what you started with. But everything else, like you said, is going to be the same. You're going to have the same intervals, and you're just adding them up in reverse. Everything else is going to be the same. So what happens is when you flip the bounds around, you get the negative of what you would have gotten the other way. So doing it in the reverse order does make a difference. It makes it a negative. And if you think about it that way, let's say A is here, and C is here, and B is there. Think about this argument. The integral from A to B is that area, plus the integral from B to C. So if I take the integral from B to C, this area is going to be negative. And so if I add those two together, what do I get?
A to B.
I get A to C. So that's what this is saying. This quality works even if B is not in my interval. Now, be a little careful because I don't know that my function is positive, right? So certainly this is one example where it works, but it turns out even if you have a function that's positive or negative, that process still will work. We think of it as area, but it's really this sort of net area. If f of x is an odd function, what's the integral from negative a to a? Now remember, what an odd function is symmetric to the origin. So what happens if I go from minus a to a?
0.
I'll get 0, because it'll be symmetric. This piece and this piece will be exactly the same. Now if I go from minus 2 to 1, all bets are off, right? I don't know what that's going to be exactly. But from minus a to a will equal 0. And I will warn you, this occasionally pops up when you're trying to find some of these definite integrals. You'll be faced with some really difficult function in the middle here, but if you notice that the bounds go from, say, minus 2 to 2 or minus 3 to 3, that's like a little clue to say, maybe my function is odd, and the whole thing will end up being 0. I'm sure I will remind you of that on a future homework, right? You'll get stumped and be like, I don't know how to do this one. I'll be like, that's because it's going from negative to positive.
How do you know if it's an odd function?
So odd function you can test if you put in minus x, you should get out the negative of what you started with. But some classic odd functions are the sine function or an x cubed function. So those pieces make it odd.
Chances are, if we see an integral that goes from negative to that value to the positive, it might possibly be.
It might possibly, exactly, that's a clue. So that combined with some function that we don't know how to work with.
Okay.
That's the combo. That'll come a little later, I'll remind you again. Okay. So right now, we have two ways to evaluate definite integrals. So one way is the definition. That's what we worked on Monday, using the sum of the i's and the sum of the I-squareds and that process. And that is something that I want you to be able to do. I will keep it to basic polynomial functions, like we talked about on Monday. Anything beyond that, the definition isn't going to work for us. It's going to be too complicated. The other way we can evaluate definite integrals is by looking at geometry. You know areas of certain kinds of shapes, basically rectangles, triangles, circles. So it's possible that if I give you a function, you can find or evaluate the definite integral by just knowing what the shapes are, right, and adding up their areas. So an example of that would be, let's integrate from -1 to 2. Let's try 2 minus, let's say about 3 minus 2x. So we could go through our definition, and you would get the right answer, right? You'd find delta x, you'd find x of I, put that into the function, calculate. Assuming you did things right, you get the right answer. But you can also recognize that this is just a line. It's 3 minus 2x. Oh, that's a little bit of a pain. Sorry, let's make it a little easier to start with. Let's just do 2 minus 2x. Just gives me a nicer numbers to work with. 2 minus 2x. What that looks like is a line. It has a slope of -2. It looks like this. So what we can do is we can think of this definite integral as the area under the curve. Now you have to be a little bit careful because you want the area, remember when you do this definition, you're adding up the heights times the width. So when you go from -1 up to 1, you're going to add up all of these heights and widths, which is going to give you this triangle. And you can find the area of that triangle, right? Area of the triangle, base times height. This is 2. How do you find this height? Yeah, this is at -1, so you plug that into the function, and I get 4. 1/2 base times height, so this area is 4. But I want to go all the way up to 2. Again, to find this height here, I put in 2. 2 minus 2 is minus 4. 2 minus 2 is minus, 2 minus 4 is minus 2. Too many 2's. And this is 1. So 1/2 base times height is 1. But that's going to be a negative area because it's below. So I know but that's going to be 3. Don't draw it just like a big triangle. There's sometimes a temptation just to draw a big triangle. The definite integral is looking at the height, so the distance from the function to the x-axis, right? You're always going back to the x-axis, so that's where your regions should be. So if a question asks you to find or evaluate the definite integral using geometry, it's asking you to do something like this, right? Break down your region into triangles, rectangles, possibly circles, and you'll see some half circles, semicircles. You can find the area of those as well. That's basically it. We don't know the area of anything else. So this is okay, right? We can find the area using the definition, hopefully. We can find the area using geometry, but that's pretty limited, right? What if my function is the sine function, or an e to the x, or a natural log of x, or even a square root function? Neither of these are going to work. We're going to need to work towards something better, some way that's going to be more versatile. And that's what we're going to cover in 5.3. But we're going to set the stage a little bit with a group work here to help us start thinking about some other ways of evaluating these definite intervals. So before I do this group work, I do want to do one more example using the definition. So let's actually, I think it's reasonable to do this one using the definition and verify that we really do get the same area, which is 3. And it's a little bit like when we started derivatives. We had a definition, and then we started to learn some shortcuts. I am going to ask you to use the definition, but it will be straightforward, right? And we'll sort of expand our work with the shortcuts. So don't worry that this is going to become more and more complicated for us. So the definition, we know what it is. Limit as n goes to infinity of the sum from I equals 1 to n f of x of I delta x. We should know our process here as well. We need to find the delta x and the x of I to get started. Yeah.
5.3 or is
We're not. So this is just 5, this is still 5.2. So the definite integral is 5.2. The area idea is 5.1. I've kind of blended them together. This evaluation is actually in 5.2 as well. 5.1. So we'll start 5.3 on Monday. So our region is from -1 to 2. So delta x is going to be 3 over n. You can subtract them if you want to, or you can just know that's the length, which is 3 divided by n. Should be minus -1 over n. 3 over n. And my x of I is my starting point, which is -1. Plus 3 over n times I. Think of that as like my clicker, right? That's like click, 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 click. I move through this region -1 to n by taking these steps of width 3 over n. Okay, what now? We plug those values into our definition and into our particular function. So this is the limit as n goes to infinity of the sum from I equals 1 to n. 2 minus 2 times minus 1 plus 3i over n. That's f of x of I. Right, this is my function. So instead of x, I'm putting in x of I. And then I'm multiplying that whole thing by 3 over n. And I would argue that there's no reason everybody can't be 100% successful getting to this point. If you know the definition, you're just plugging values in. It's a very straight formula. You plug things in and you plug it all into the function. And now there's just a little algebra. I just need to simplify this. You can do it in a number of ways. Plus 2 minus 6i over n. So that's 4 minus 6i over n, which gives me 12 over n minus 18i over n squared. There's nothing new about that. It's just manipulating an expression, right? I'm just multiplying the pieces around. You just want to make sure you multiply it all out, everything out, so I have just a sum or difference of a couple terms there. So now there is a little bit of new stuff, right? Or summation work that we have to do to evaluate this. But I would argue that going from here to here is something you should all be able to do. Nothing magical at this point. Now, here is where we have to work with sums a little bit. That's a new topic, so there's some room for misunderstandings there, right? But we know from sums that we can sum both of these pieces individually. This is a constant with respect to I. So when I sum a constant, what do I get? Yeah, I get that constant times n. Don't forget that you multiply it by n. It's one of the most common mistakes people make. So they sort of just say, oh, it's a constant, so I just get 12 over n. No, it's got to be 12 over n times n, because you're adding it up n times. 12 over n plus 12 over n plus 12 over n plus 12 over n. And then I'm going to sum the second piece. The negative 18 over n squared is a constant. So I pull that constant out and then I sum the i's. And this is where we have a little formula, right? The sum of the i's. You can remember?
N plus 1 times.
N times n plus 1 over 2. The I squareds is a more complicated looking formula that has 3 pieces there. I'll give you the formula for the I squareds or the I cubes if we run across those. And here again, I would argue this is not anything new. This is something, if you look at this as its own problem, this is one we did way back in the beginning of the semester. It's a limit as n goes to infinity. This is 12. 18n squared plus 18n over 2n squared. Which is 12 minus, what happens, right? I can take both these limits separately. This limit is 9. Because you're just looking at these leading terms. They're both n squared. This n term here doesn't matter. When I look at those, it's 18 over 2. Which is, of course, 9. 12 minus 9? 3. Now, clearly, the geometry is easier, right? But that's because it was an easy function, right? It's a linear function. You can do that with geometry. If it's an x squared function, geometry doesn't work for us. We don't have any formulas for parabolic sections. But this definition turns out to be not really much different, right, if it's an x squared. An x squared is going to generate an I squared instead of just an I, but it's the same process. How do you guys feel about that? Feel like maybe complete some of those? As I mentioned on Monday, they are all fundamentally the same. They can look a little messier with the algebra parts, but they're all going to be the same in the end. Not that it matters so much, but the complications, the things that make it a little harder, if you don't start at 0, it's a little bit harder, because then what you're putting in for x is 2 terms, and that just makes the algebra a little messier because you have to distribute, right? If I started at 0, it would have been a simpler kind of problem. So when you see them that start not at 0, you have to recognize, oh, that's gonna give me a little bit more of a complication to work with. Okay. Questions? Any questions? Yeah.
So what happens to the other end? Yeah, that,
Here?
no. Down there.
Like this? Yeah, so what happens is if we actually went and did this limit here, the process that we would have done when we did these limits at infinity was we divide top and bottom by n squared. So that gives me 18 plus 18 over n all over 2. And what happens is as n goes to infinity, that piece goes to 0. So I end up with just the 18 over 2. So the shortcut is to say, well, I don't have to actually do that division because I know what's going to happen in the end. Any smaller powers of n, whether they're constants or n's, are going to go to 0. If you do this process correctly with your formulas, each of these individual pieces should have the same powers of n on the top and the bottom. So this is like an n over n, which went to a constant. This was an n squared over an n squared, which goes to a constant. If you had another term, you might have n cubes over n cubes, which should go to a constant. So if you're missing, if you have like an n cubed on the top and an n squared on the bottom, that means something went wrong in here, right? You just didn't distribute or forgot one of the pieces. So that's a little bit of a check on your work. Yeah?
And for I, so I'm guessing that n times n plus 1 over q.
Yep.
How did you get that?
So that is a formula. That is equal to this. So that was that, like 1 and 100 and 2 and 99 and 3 and 98. That formula is this. Okay. So the other formulas that you might run into, the sum of the I squareds is equal to n times 2n plus 1 times n plus 1 over 6. And the sum of the I cubes is n squared times n plus 1 squared over 4. They just are. We can check them. If you sum from I equals 1 to 4 of I cubed, this is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. 1 plus 8 plus 27 plus 64. 91. That's 100. The formula says the sum from I equals 1 to 4 of I cubed is going to be n squared times n plus 1 squared over 4. 16 times 25 over 4, which is 100. Sort of easy here to do one or the other, but if it's from I equals 1 to 20, this formula is way easier. So those formulas, we didn't go through why they work. They're more complicated to show, but they are equal. And I will give those to you, so you don't need to memorize those. But you'll bump into them all the time when you're doing this process. If you see an I squared that you're summing up, you're going to replace it with that.
Why
Yeah.
do we consider 12 over n a constant, and why do we multiply times n?
So, because imagine I sum from I equals 1 to 5, 12 over n. Well, when I is 1, that's 12 over n. When I is 2,
Oh,
should have picked a smaller number than 5, right? But so when you add them up, you get 5, 12 over n times 5. So if I go from 1 to n, I get 12 over n, 12 over n times n. So the thing that's changing is the I. So if there's no I in it, then it's constant for that expression. So, good questions. Anything else? Summations are like a new thing for many of us, and so new things are always, it's unclear how they work, and we're not giving ourselves a thorough treatment. There are lots of other properties of summations that we don't need, right? So we're sort of just focusing on the basic properties that we need for this one problem, which is an important problem for us. Okay. All right, so we've got a good time here to work through this group work. I will go ahead and break you up. And some variety here. Let's do 8 groups. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1 and 2. So let's go 1s up here, and 2s, and 3s, 4s, 5s, 6s, 7s, and 8s. I literally got finished it all.
Yeah, 4, 5. Okay. All right then. Everyone.
What's that?
Yeah. Oh, yeah.
Okay, so the goal here is to start thinking about a new kind of function, which is the area function. And so the reason I'm doing this is we're trying to preview 5.3. So 5.3 is called the Fundamental Theorem of Calculus. It's a big deal. We've been working towards it basically the whole semester. All of our theory and ideas and the derivative and the area stuff is all coming together to sort of try and tell us a new way of computing the definite integral, right? Because the definition and geometry are both pretty limiting. They don't allow us to find the definite integral of other functions that we might be interested in. So the fundamental theorem is going to give us a new way of doing that. But in order to understand how that theorem works, we have to have an understanding of something called this area function, or I call it an accumulation function. So just as a couple kind of warnings about this group work, this first picture that you have here, the x is your upper bound. So the x, imagine, is moving around, and you're computing different areas based on where that x is. So the scale here is not quite right. Like if you go from 1 to 2 for this first one, right, obviously where the x is drawn is not at 2, right? If this is 4, then the x should be, over here. But you can find all of these values. Don't use the definition. For all of these definite integrals, what should you use? Geometry, right? This is just a nice square, right, or rectangle. So use geometry, and this is true for all of the parts of this group work. Use geometry to evaluate those. What you're going to do is find various definite integrals using geometry. It would be quite simple. But then you're going to try and come up with a function that depends on x, the upper bound. So as the upper bound changes, the area changes. And I want you to come up with a function, so some formula that's going to compute this given any x. Okay? So that's your job. And then in D, you're kind of reusing what you did in C. Once you have the function, you're just going to name it a of x. You already found the function up above in C, right? So you already sort of did, I don't know, sometimes people, when they do this group work, it's a little bit confusing. It's repetitive, kind of C and D. So then what you're going to do is you're going to repeat that process for two other functions, right? Again, using geometry. Again, using geometry, these are triangles in this case, and again, coming up with your function. Right, so you're going to work through all of those, and then eventually we'll come to our sort of punchline, which is here. All right, so at that point, I may check back in with you. And if we get done with all of that, then you can get started on the back page. Right, the back page, just more sort of typical problems about the definite integral. Okay, so I'll let you get cracking on these areas using geometry.
Or here.
Which is basically the x. Makes sense.
I understand what we're doing. I do understand what we're doing. Talking physics is doing one more. First one is I wrote it down. So, all of these.
So-
we're just finding out the height,
So this,
like the
so
rectangle,
here,
makes sense for before, the other one, so because there's that number is always one, it's, so for that first one, it's 1 to 2. So, this is just gonna be like one, and the area's gonna
that's
be
the only area.
rectangle, and then as you go farther in, the formula for this
Well,
would be...
check the width though, if I'm going from 1 to 2.
The width is 1 and then 4 times 1.
What? So it's just, it's like this region. That's bigger than 1 and 6. Probably like right in the part.
Yes. It would be that.
Yeah,
And then B is gonna be X minus 1.
Right.
For everyone, it would be.
Or is that a T?
Yeah, that's a T, but it's...
Is T just from it?
4 times X minus 1. Yeah.
Okay, yeah.
D is representing the point from the project. It's representing that X there.
Yeah, so it's really things, no, so, because it says here, you took about these numbers, you took about this number. So it's just, it's a simple function of y equals 4, so it's just, it just goes all the way to wherever. The height is always going to be 4. Yeah. So for any,
And then solve it for kind of like how we did geometry. This is now not doing it geometrically, we're just doing it to. It'll be 12 yeah, I guess it's having its, I think it's having its balance. Because we technically did it geometrically. And now it's like, hey, use the definition and verify it. It's like 4.
Restart on 1.
Yeah, I got it.
So we're doing 1 to 2, okay, so that's a 3, 4. So that's just our starting point, it could be 0.
Does it work?
I'm like really confused.
Exactly, it's for these, right?
ABT, okay.
So it's the same thing, so from 1 to 4, this one.
So that is your function, and that's really, that's really what you want. That's part of D.
0.
Yeah. Because I was entering X as like a variable. I didn't realize that it was
Then you can, yeah.
4 times.
Yeah, it works. It's got a function, it's got the same values every time.
Where it's universal.
This is exactly what we did.
Yep, 4, 6, 0. The original definition.
This is like exactly what we did. So now we know.
No matter what, you just multiply it.
Yeah, it looks like X is changing here as well. It's like an AS2 and then
This would actually be really simple because.
and then it's going to might be 1 and 5. 4. Looks like if it's, or you multiply it by 4 times, and it looks like X okay, so then I guess we just have to turn. Yeah. If I understand correctly.
That would give you,
So right, like,
Yeah, you just plug that into the
one would be zero, your function. Yeah, it's the function that we
so then A of X is just 4X.
Because that's the function, it's asking, come up with a function, and it's use that function.
Yeah, well, they're basically finding a point over here, and plugging it into f of t. So like f of 0 would be like 2 times 0 plus 2, which is 2. Yeah, and that's what we got here. Then you're just saying, if it was a negative 1, but I'm getting 0.
Well,
2 plus 2 in order to, because that doesn't make sense. Or I guess it does, so it's just take all the triangles and then you got the area of this. So, oh, we're using the base times height.
So when they're talking
Yeah.
about.
I was like, what am I forgetting?
Use it every time. Just to throw out universal.
1/2.
Yeah, so what they want, don't use the definition, they should area limits. Well, what we want is a formula, like what about 1 to 5? Or like area.
So yeah, if you put in four, because this is exactly one. If you find what it is,
Yeah,
you
you
gotta
go-
get the area of this whole thing, and then you put that formula.
What's the area from 1 to 6?
Okay, so, yeah, the way I thought about it, you're always gonna have 4 to get this.
Sure, so what's the area
And
from
you
1
look
to
at
6?
4 times.
Yeah, I was trying to like X,
4 times X.
figure out, Ray's trying to use that formula that takes
That's all.
Yeah, now in
Like
because
here.
this would be 2 horizontally, sort of vertically,
This would be just 1, this is X.
yeah, and then
your function is
2 times.
2 or 3.
So that is your, like, area function, right? So if I give you any upper bound x,
And then you got
oh, so that's formula.
Yeah.
That's really our answer here, and that's really what.
And the big triangle here, this entire triangle is here.
And then you subtract from that.
And this one, right?
This was all within.
Right.
So this is. So when you're.
That'll give you, it should give you the same, and then you should get 1 to 2.
So.
That's what AFX says, the area from 1 to 2.
So if I think about it,
So you're just calling that function AFX.
have everything.
Put in 2, so 4 times 2 is 2.
And then you can find those, it's not that exciting. So, yeah,
This line is
but
here.
but you're now you're gonna repeat that
Base
process.
times the height.
With a different
Base
You're
times the
gonna
height.
find the area a couple of times,
You
you
use
can find the
the
pattern,
2T
you can find that formula.
Yeah, you use that in the formula, so.
Perfect.
9 minus 1.
The reason we did that is
Yeah, they
because
just
you're
keep
able
changing.
to figure out what
And we just took the smaller triangle and subtracted it.
Yeah, don't worry about that. It is true. So like, this is saying that this function is only worth negative 1 and 4. We know that this one, more far out. So this is why don't worry about that. Just that. Now you can go, don't worry about it. Negative 1 to the next.
So this small triangle area will always be 1, no matter what number you put in there. That triangle is
Evaluate it a couple times, you can try and find a pattern.
But now, when you plug in 2 for that, 2 equals FT times 4, they want you to find FT. And F of T is T minus 1. So T minus 1 times 4. If you solve for T, then it's 4 plus 1.
24?
Yeah.
X over 4.
Okay, and this is true, this is like the line is going.
And then I think they were making kind of like
When you
one
compute this,
for C.
let's say that we went from this here to this. Which may be the complication. Something like that. So. What I do, or what I do, the equation is known area from 1 down to the lowest area.
Yeah.
We don't want
1/2 times base equals 1.
Yeah.
Yeah.
base.
Base.
Yeah, so, this is, we solve for F of T. Take this one,
And then we store x equals 2 into like 2.
X equals 1, you convert the 1 over here and whatever x is. times,
And then we could find area
two,
triangle.
Or FOT is actually closer to
you could do it that way, and then subtracting. Yeah, because that way that's also.
And then we don't want this little, so 9 minus 2.
What do you get for the area of the first one?
Same thing, you get a different X. X is represented in the
Oh, okay. It's really this. No, I would say. What is this?
Yeah.
Your
Function,
function.
it's just naming it this area function. So, but it is a function of x. So t is sort of this relationship. X is your upper bound. So if you really do want like
We
various
calculate it
coordinate
into
x,
two ones,
it should be,
and then you're just subtracting whatever this, you're using that to find
this should be in terms of
and then you just subtracting
so
this
your area from one to x is like counted.
subtracting this from the whole area.
Right, so that function is just, and then for the area, x is the upper bound of the area.
Area of this little times 2.
Right there. So the area is
Oh, and then you
determined by how far away you go, right? The farther away you go, the more area you get. This formula, which is one thing of all of it, is what tells us that. So a of x is
So you
just
have to
our
plug
area
in,
function.
the x into this function, the other, so it'd be x plus 1.
So these, yeah, you just put into.
Yeah, because you have to times the area, which will be
The area up to 2, or the area up to 2.5.
times 2.
So that's what that is. So,
Okay.
E is basically the same right now,
it's
so
in a different form.
this is really kind of what our goal is. An area function for this scenario.
I got
So now you want to
24 and 0
repeat
back.
that
You guys
process.
got zero for those.
Yeah, we're in 24. Second scenario. Now you've got a line, you're still trying to find areas, so you start by finding the areas at a couple of x values. But your goal is to find a pattern, so you can find the area for any x.
So now we're doing the same exact thing, but we don't necessarily need to subtract the smaller triangle because it's a part of the balance there. Yeah, because over here was like 0, this is negative 1, so we don't need to subtract and then we can just start x, right? It's the same formula, except we just remove the negative.
Again, I just took this as a whole. Right.
This
Plug in.
point, the point where
4 here.
goes from positive to negative.
Oh.
Right, and then you multiply 10 by the actual number of pieces you're taking from the original, from where there's, divide by 10, and then you take that part out, then it is, because I think it was
For it to be a negative area, it has to be y equals down here.
I just think
And then you're going to go to so area.
Like, I was wondering.
Again,
So, 0 to 4. He found
Just taking the second, it might be x, yeah, okay. We were right.
So what you're doing is you're getting the area of this, or you're getting the area of
Yeah.
So you're really finding and then subtracting. Yeah, I got 24 too. But I just did it at different methods. Yes, and then you just, because that's kind of the concentrate all that they want. So then we can have the,
Yeah. Where to the next part? Well, I guess we have to look at it first before we worry.
But that's how I feel about that one too.
Oh yeah, that, we just broke it down so it's easier.
Yeah.
So this one is, I guess, instead of a graph, we're just getting like different, yeah. So if it's about the derivative, so that's 0, that's 2, that's, and you're gonna be it's always gonna be like a constant, but
Yeah.
a bit ahead of me. I don't know what it's trying to have us see. Or wait, I think it needs us to calculate the area equation and then find the derivative of it. So like kind of like, so these are exactly the same equations that we used. So we could just, yeah, so we could take the formulas for those. So 4 times x minus 1 is the 1 for ax. 4 times x minus 1. And then this one is 2.
plus x squared.
And then, yeah, that's the 1 half.
So let's test them out.
So can we compare those?
So he's
Well, he said he was gonna jump
Yeah,
when
'cause
we
it's
get
the
there,
same
but
thing.
why not, let's do it and then we'll see what. I think we can grow that way.
So 2x is
Okay.
and then 1 over 2x
So we're basically getting.
Oh.
Let's see. We're in.
The lower bound is always 0, and, the upper bound is probably 2.
So what I did was 2.
So,
Upper bound.
so for any x value,
This
it
one starts with
would
1.
be 1, t starts at 0, add 1, give it 1,
No,
4.
we're adding the 1.
Here comes the x value, and then
Oh,
this
no,
just put a function x, so you're, yeah, this one I negative 1. Well, I just multiplied the polynomials before I give the derivative, so I think that'll be 0. So it was like 2x, 2.
Actually, the area.
Well, yeah, no, that's actually. Is the main function down here. I see how strange it is. That would actually, that actually work. We probably just wrote it on the page and we're just used to that.
Like, oh, half of it.
So that is, that
and
actually
then
might
the
go
other
from
half.
start to. Yeah, it's not gonna make a difference.
B and C, they're basically.
Oh, sorry, I didn't have plus. I think they are, the only thing is -1. I use that -1 to subtract the constant, which is always gonna be 0. So it's gonna be exactly the same.
Yeah.
So basically f of t
That's all I have.
the derivative. This is the antiderivative. That's what this is.
You do 1/2
Yeah.
base plus
I guess it's it equals everything.
then you can subtract antiderivative. So the main function
I
equals
took my class online.
The antiderivative
Summer,
of the other function.
and it was,
So,
I mean, I had it correct.
I think that's what you're trying to have us say. Does that make sense?
Yeah.
Right.
Yeah. What are you writing about? Plugging of
Yep. But here's like one touch.
Yeah.
Area function.
That's what I actually got
We get here. I mean, this one's, I knew this is all of the so this formula would be. Then there's something. Then age is the time. Yeah. And then, yeah, so that'll basically the same, because at the end of the so we get always derivative of constant. And then 4 is now that we know that, what is this really complicated function? We're gonna add a derivative, and it's gonna be so that would be that, whatever, the derivative of that.
Yeah, so it's just gonna be this.
I was like wondering what I was, because I'm not in the and I'm like, oh, like, this first one.
Yeah.
Just 2x plus 2 times x plus 1 or 2.
Sorry. Oh, I basically said that f of t equals 8 times x. That basically the main,
Divided by 2.
the f of t function equals the antiderivative of a to the f. So that's what I basically said. Because I think that makes sense, based on like what we've learned in 4.9.
Okay.
With the antiderivative, that's basically what this is. And this function here is a function that you're trying to get the antiderivative from. And that basically correlates. So that's how I think it. And then 4 is basically of that function. No. Well, it's asking. Oh, yeah.
So this is just, show me what you guys saying.
I think it's gonna be what.
I'm looking at patterns, right?
This part is.
1/2 base times height.
Yeah. So I think, what would it be then? Would it be?
Minus
the
1.
Oh,
Big
okay.
triangle minus a small
Because
triangle.
this is like for
1/2 base
we don't
times
have the
height
function, so we can't.
minus
see the
1.
function. But if it was written.
So
in
1/2 base is always x
Then
plus
we
1.
know that.
The height is always f of x minus 1. And then this, if you just multiply through the
Well,
1.
that's what I thought too originally, but that's basically going from B to this. And we're not the same thing. So this, we need to get the derivative.
You check your work here.
It said what f of t equals. Or sorry, if it gave us the derivative, but it asked us what does that mean f of t equals, then we know that.
Yeah, so we got the right one, we just.
No, that I, yes. But this, it's not giving.
Oh, that's on the second page.
Yeah, so right
Like
now it's basically giving us the second, the area function, and it wants us to find the derivative. This is giving us this one, the area function.
Yeah.
So we're starting.
And we need to get the derivative of it, and then from that derivative, we know where the function is. That's what it's trying to say.
This area
Um,
over here.
I just don't like. So big.
Now, it's a 0.2 triangle. This is minus this function. So it's just, you can get any triangle.
I'll try to figure it out, because basically if we look at the main function and then the area function, it's somewhat broken up.
Now,
Oh, no, never mind.
Oh, because we're including.
Wait, you're including this. I know how you took it.
I don't want to do this derivative, I just want to
Yeah. So is this saying
dx is d of x is the area function. D of x is the area function for that crazy curve.
Oh,
I see,
think about it.
Yes.
This derivative of this?
But wouldn't it be?
Well, think about what d of x is. V of x is the area.
Oh,
The area
and the other, that's just
The original function.
So the other one was like
derivative.
So in order to find the derivative of the area function, you don't even need to know exactly what d of x is.
But can I just say, equals
Because the pattern is
so we don't have to solve.
well, you have to find the derivative, but you may not need to do all the intermediate steps.
Okay.
She really likes me, and I have a good grade in class, so.
Okay, let's check in here, right? Once you've got b of x, c of x is almost the same, right? It's just you don't have to subtract off the little triangle in the beginning, because you're starting at minus 1 to x, right? So you're
I'm
going
not
to do
even gonna do it.
the same sort of formula, you just add 1 to your b of x. Okay. So here is the big, the punchline, yes. So a of x, if you go back, is 4x plus 4. Is that right? No, 4x
4x minus
minus 4. I should have done that. 4x minus 4. b of x was x squared plus 2x. C of x was x squared plus 2x plus 1. Okay, those are, what those are area functions. I call them sometimes an accumulation function because they're gathering up area, right? As I move, as x goes farther, these are gathering up more area because they're positive functions, right? If the function was negative, then it might start subtracting area. But in any event, it's accumulating area. And so now they're just asking us to find these derivatives. They're pretty trivial functions, so we can definitely find their derivatives. And so here is the big deal. There is an interesting fact about the derivative of the area function. What is the derivative of the area function?
It's always the original. function.
It's the same as the original function. So let me remind you of what we covered on Friday of last week, which was if you have a function whose derivative equals f of x, what is this function? It's an antiderivative. Now, you guys are spoiled by brilliant observations, right? Because you're in school, right? You see all sorts of amazing things. But this is a really amazing thing. Because what is the derivative in general? It's the slope of the tangent line, right? It's the rate of change, all of this stuff. What does the derivative have to do with the area function?
Like how it's changing, possibly, or?
Yeah, it's definitely related because we're saying that the area function is the antiderivative of the original function. It feels like those should not be connected, right? The derivative is the slope of these tangent lines. The area function is, we did these with geometry, but really they're the limit of the sum of these rectangles. What this is implying is that those two things are not just related, but they're almost the same things, right? The antiderivative of the function is the area or accumulation function. That's a really big deal because these were easy to find because of geometry, right? And they were simple functions. But what if this were x or t squared? We couldn't find these directly because we don't have geometry that would allow us to calculate those. But we know how to find antiderivatives, right? You can find antiderivatives of a whole bunch of functions. So rather than trying to use the definition or the geometry of the situation, it is implying that we can use an antiderivative to figure out what's going on. And so this final question here in part 4 is here we have a function that is extremely complicated. We don't know how to find that using geometry. We don't know how to work with that using the definition of the definite integral. We don't even know hardly how to work with that using derivatives, right? Or certainly not antiderivatives. That would be an extremely complicated thing. But we know what the derivative of this function is going to be. The derivative of this area function is going to be the base function, which is this thing right in here.
That's what I was thinking.
Now it's that function evaluated at x. Right? Because the x is how far I've traveled, right, from 0. So the area that I get depends on the x, not the t.
Oh, actually, it's not complicated.
So this is actually amazing, right? This is an incredibly complicated function. The base function is super complicated, and then we're taking the area of that function from 0 to x. But we know how to find its derivative. We know what the derivative of this very complicated function is. And if we know the derivative of it, how can we find what this function is? Take the antiderivative. So if we could find the antiderivative of this, we would know what this function is directly, right? Without thinking of it in terms of area or geometry or the definition. So this is actually the fundamental theorem of calculus, that the area function and the antiderivative are in some sense the same thing. And knowing that is going to allow us to find these areas without geometry and without the definition. We're going to be able to find these areas directly by using antiderivatives. So that's the big deal. That's what we're going to prove on Monday, that actually does work for us. It's not a super complicated proof. We've done all the work before to get here. And then we're going to use that. I do not. I did all. I gave you all the answers. I know all the answers. You know all the answers. So you don't need to turn these in, but I will mark down that you guys worked on them. So I'll give you credit for the group work. And then have a good break. Be safe. Be nice to your families. See you on Monday. Yep. That's right.
Like, we don't get instead of Thanksgiving.
Well, I think this is so.
Every time I'm not on
It is equal to my original function here. These are just area functions. So the derivative of this area function the equivalent derivative of
Joy. Stickers and wheels. Joy to work with.
You're not the first one to make that one.
We know that
I was thinking that I'd get really frustrated.
the derivative, I know what the derivative is.
Oh, yeah.
So what that's really saying is that this operation, finding the definition, somehow the antiderivative.
Last night, I was just making
So
one
you do it
Like what's the what?
like a leaf.
Yeah.
It's kind of onion.
They would mutilate it, right? Limits and some
We use like a false mean onion. Have you ever seen it?
Monday, we'll see.
Similar in a way.
Related to
It's about yay long, about yay wide. It's white, this is like coming up, and then the leaves at the end are green.
Okay.
Spelled L.
So,
All the leaves.
So it's 5.3.
Yeah, I know. It was 5.1.
Yeah, no, I'll post 5.3 should be open right now. And then, I can post that. Oh no, yeah, okay, I can post 5.3.